Okay, so function composition and inverse functions. So here we're going to look at a particular kind of composition. So last time we had a function f going from x to y and a function g going from y to z. So we had that middle set in common and we could make the chain x to y, y to z. Now we're going to look at it a little bit differently. We're going to have a function going from x to y and then y back to x. Okay, so I hope you see that looping behavior there. So we've got here from x to y. From x to y, we can go via f. From y to x, we can go via g. So the idea for an inverse is that if we start with an element in x, we can go over to y using f. We can go back using g, and we end up at the starting place. But that's just one way. There's another way. We can start with an element in y, we can go via g, and then go via f. Okay, in high school you didn't go both ways. Okay, so now we go from x to y back to x, and y to x back to y. There are actually two inverses. We have a left inverse and a right inverse. In high school you only did the inverse. We will see the conditions to have one inverse, not a left inverse, not a right inverse. Okay, so let's say we start in x, we go with f, then we go with g, so it's g after f for that direction. So g after f of x, and what do we want? We want to end up back in x. So this must equal x. So g of f of x is equal to x. We call this a left inverse. So we've got a function f. G is a left inverse because we get back to x. Did everyone see that? Good. And we can do the same thing going the other way around. We can start at y. We can go with g and then back with f. So it's going to be f after g. It's the other way around. Remember I said the order matters. So we're going to have f after g of y now, not x, because we're in a different set. We're going to call it something else. So we can write this as f of g of y, and we want to end up back at y. And here we call this a right inverse because it's on the right-hand side. Okay, so we got left inverse, we have right inverse. Now to have the single inverse that you know of, there's two conditions we must have on f. If we don't have the two, then we either have a left inverse or a right inverse. And then for homework, there's some examples to check that. But for it to be a full inverse, a left inverse and a right inverse, it must be injective and surjective. If one of those is missing, you're looking at either a left or a right. You need to have both to have it being an inverse. So for f to have an inverse, so just one inverse, not left, not right. F needs to be injective, and we know what that means. Okay, so you know what injective means, you know how to check for that. So if I give you a function, you can check if it's injective. And surjective. Right, you need both of these conditions. If you have both of these conditions, then we can write this g which was a left inverse and a right inverse, as f with the little -1. You would have seen that before. Okay, so if f is both injective and surjective, then we call it bijective or invertible, same name. You can think of just remembering this bi, means two. So it's the left and the right. So two inverses, one side and the other side. We call it bijective or just invertible. Okay. And if that's the case, then this g over here, being the left and the right, we give it the special name with the f for the little -1. Okay, it's not a power or an exponent, it's just a symbol. We call F inverse F with a little -1 there. Okay. So that takes care of the G being the left and the right. So we can replace those two equations with F inverse after F of X is X. You can check this condition and obviously the other one because this is a left and a right inverse. And then we have F after F inverse of Y sends us back to Y. Okay. So here this takes the role of G. So on that side, it's the left inverse and it's the right inverse. So it's bijective because it's both left and the right. Okay. Let's have a look at a quick example. Okay, y equals x squared plus 1. So we're going to look at the graph of this. We're going to determine when it's invertible, because we'll see this is this surjective? Oh, we don't know yet. I never said what the codomain was. Remember, domain, codomain, then we can check. This is just the rule. But is it injective? We can check that. Is it injective? No, it's 2 to 1. It's not. Okay. So let's do a quick sketch, and then we'll work out the domain and the codomain for it to be invertible. So here we have y equals x squared plus 1. And notice, as we said, it is not injective. It is 2 to 1. What we want to do is find an inverse for this. So in order to do that, we need to cut the domain. Okay. So what we do is we look at this portion, this negative portion, and we ignore the rest here. Then it becomes injective. You see that? Yeah. So if we only include this part, this side will be injective. If we only include this part, this side will be injective. You see that? In high school, your teacher might have said the branches of the parabola. Did you hear that? The left branch, the right branch. That corresponds to the left inverse and the right inverse, and so on. Okay. Okay, so let's ignore the negative side, and we're only going to focus on the positive side, where we know that this is injective and surjective, and so invertible. So I'm going to define the function f only on that positive side. Okay, so what should the codomain be for this to be surjective? For it to be surjective, codomain must be equal to the range. Okay, so what's the range? 1 to infinity. Good. And we're going to send x to x squared plus 1. You see all the extra details we have to fill in with university compared to the high school. So in high school, you would have just done, you swap x and y, you solve for y, done, right? Yes. No, it's a little bit more technical, but this is very important. Okay, because you can't just swap and solve. Well, which side are you talking about? This thing is not surjective. It's not injective. You need to pick a side. This is picking the side. Your teacher would have said, do the left branch, do the right branch, right? That's what they meant. They meant restricting the domain, and then that means left branch, right branch. Okay. So we're going to focus on this. This will be the right branch, as your teacher would have said. We want to invert this. Please note the domain and the range. We'll see later on they actually swap. Okay. So your teacher didn't lie about the solving for x or y and so on. So we'll do that. However, we don't need to swap x and y. That's unnecessary. So here we have y equals x squared plus 1. There's no need to do that swapping. That's just some high school thing that you did. We're just going to solve for x as is. Okay. So first, let's take the 1 over to the other side. So we have x squared is equal to 1 minus y. Okay. Everyone clear on that part? Sorry, y minus 1. Wrong way around. y minus 1. Okay, and then we do the root. But remember, the root has that plus or the minus, right? Again, that's with the branching. And we're going to check which one we choose. So we have x is equal to plus minus root y minus 1. Now we can't have both, otherwise it's not a function. But remember, back up a little bit, f goes from x to y. The inverse goes from y to x. It goes the other way around. Now let's have a look at what we wrote here. F goes from x to y, and g, or f inverse, goes from y to x. So this is the output for the inverse. The output is always positive. So which one do we pick? The positive one. And you'll see something quite interesting in a bit. So here we started at y and we end up at x. That's f inverse. So this x we can write as f inverse of y. Now, what makes all of this extra work that we did here necessary is, let's look at this function, f inverse. What's the domain for this? Like I said yesterday, domain range you must be able to do quickly now. Everything greater than 1. Okay, so this is for y, is everything greater than 1. Let's have a look at the range that we calculated earlier. We already know the domain for the inverse. Okay, it's exactly what we put down earlier. It was even before we did the calculation. We knew the domain for the inverse. So do you see why it's important to specify the domain and the codomain? Because when we're doing problems like this domain that we calculate or we're given becomes the range for the inverse. You did the calculation already. You don't need to do it again. And now when I said calculate the range of this, we weren't interested in the inverse. I just asked you what the range was. We saw immediately what it was. It now immediately becomes the domain for the inverse. All of that work was done here before we even started the calculation. So right back at the beginning when I said, this is not the function, this is the function, that's why. Okay. So we immediately know that this is x. It's the domain for f. It's the codomain for f inverse. This is y. It's the codomain for f, and it's the domain for f inverse. Okay, and you get it for free. We don't even need to do any more calculations. Okay, so let's write this out nicely. So we have x going to y via f. We go back via f inverse. Okay, so on the top, I'm going to put the labels for f. So x is the domain. And then y, that will be the codomain. But now, this over here, we calculated as the range. So f has to be surjective for this to be the domain for f inverse. Do you see that? Like we did yesterday with the composition. So f has to be surjective. So domain equals codomain. So, codomain equals range. Why? Well, because this now needs to be the domain for f inverse. So f has to be surjective. So that's number one. And number two, we'll see why it has to be injective. Okay, so this is now the domain. So codomain becomes the domain for f inverse. We go backwards, and that now becomes the codomain for f inverse. And we'll see now that it has to be injective for us to go backwards. So everyone see, to go from there to there, it has to be surjective. And to go back, it now has to be injective. And we'll see that with a picture. Okay, so please have this diagram written down. Okay, so let's look at a picture just to solidify all of that. So let's say we start at x. we end at y. I'm going to put down 3 elements here and only 2 elements here. So this is definitely not going to be injective because it's impossible to do that. Everyone see that? Yes. Okay. So let's do the mapping. So F, it will have to look something like this. Okay. It's definitely surjective. We did that already. But this is not injective. Everyone see? Not injective. Yes. So we go F this way. Now F inverse, we want to go backwards. Let's look at this element over here. Can we go backwards? Yeah, it's fine. We just follow the line backwards. That's fine. What about this one? No. Do we take the top one or do we take this middle one? We don't know. So in order to go backwards, that original F has to be injective. If it's not injective, you've got this 2 to 1 behavior. But if we go backwards, it becomes 1 to 2. A function can't be 1 to 2. That's impossible, right? So in order to go backwards, it must be injective. So to go forwards, it had to be surjective. We showed that earlier. To go backwards, it must be injective. So if we want it to be invertible, it must be surjective going forwards and injective so we can go backwards. Is everyone clear on that? Yes. Everyone clear? If I remove surjectivity, it doesn't work going that way. If I remove injectivity, it doesn't work going backwards, right? Yes. Okay. Let's have a look at some proofs, and then we'll leave it at that for today. Number 1. So these are just to illustrate what we've gone through. So for the tests and exams and so on, you might get like 1 question on finding the inverse, but you've done all of that before. You know, you're not going to be retested so much on that. But what you are going to be tested on is this understanding of these diagrams. Okay. That's the more important part. Solving for X is algebra. It's not so important. But the proofs, that's important. Okay, so we'll do a couple, and then I'll leave the rest for homework. And then what do you do at home? You do them. Okay. Let G from A to B and F from B to C. Okay, so immediately you can see we're going to do some sort of composition, right? F goes from G goes from A to B, F goes from B to C. Let these be injective functions. And please, whenever you're doing these proofs, you look at the words injective. Immediately you scribble down the definition for injective, right? So injective, if you don't know what it means automatically, you make a little note. After a few examples, when you make the notes, now you know it off by heart. So those are injective functions. Prove that F after G, right? Because G comes first from A to B, then F goes from B to C, so F must be after G. Is injective. So we're not dealing with inverses for this problem because we're going from A to B, B to C. Later on, we'll look at those examples. Okay, so what do? Well, a proof is always broken up into 2 parts. There's stuff that is given, and there's stuff that I want you to show. It's always those 2. From now until 4th year, you'll always see that. So what is given? We are given G as injective. And we know what injective means. We can make a note. F, we know is injective. We know what that means. We can make a note. What do we actually want to show? We want to show that the composition is injective. So how do we go about proving this? Well, we know how to show something is injective. So we start by showing that this is injective with that calculation. So we try to show this is injective. And along the way, we are going to use what is given. That's always the setup. We start with what we need to show, we use what's given, and the answer just comes out. A little bit of thinking, but it just comes out. Okay. So the idea is we write down what's given. Okay. Now you don't always have to do this, but for the first few, it's a good idea to set it out like this. So given. G is injective. Okay. And F is injective. Now, if you automatically know what that means, that's fine. You can continue. If you don't, well, let's write it out. What does it mean for G to be injective? For G to be injective, we know that if G of X is equal to G of Y, then X equals Y. Yeah, that's the definition. What about F? If F of X is equal to F of Y, then X equals Y. That's the definition. We know we can work with that. Now, what do we need to show? Okay, what do we want to show? The composition is injective. That's what we want to show. So need to show F of G is injective. Okay, now we'll go through it slowly and it should click, as soon as we start. Should. Okay, that's the key word. But we'll go through it slowly. Okay, so how do we show something is injective? Well, we use the definition there. Okay, so let's look at this. F of G of X is equal to F of G of Y. That's a starting point, right? So F of G of X is equal to F of G of Y. Right, we're just following what we know already. What is this? F of G of Y. That's a composition. This symbol here means F of G of Y. And this is F of G of X. Right. There's no harm in saying it out loud, so you get the idea. So this is F of G of X. You see how I said it and wrote it? F of G of X, F of G of Y. Okay. Now it's going to be up to one of you. I'll give you the hint. You tell me where it goes to. F is injective. We know that. So F and F here, we know is injective. So from this line, what's the next line going to be? G of X equals G of Y. Exactly. Right. You all got it. Okay. Very nice. G of X equals G of Y. Okay. I thought it would be a little bit longer than that, but well done. Second hint. G is injective. G is injective. So what do we get for the next line? Okay. Well, we did start with the more difficult problem. I think everyone's quite comfortable with this. Okay. So let's see where we started with. F of G of X equals F of G of Y. That was our starting point. Let's go back up here and do a little highlighting. That's our starting point. Where did we end up? X equals Y. I mean, that's something like this, right? Okay, from the definition. So let's write it out neatly and conclude the proof. So what do we have? We have F of G of X equals F of G of Y. That was our starting point. Then we just fill in our ending point there. And so here we're just ignoring the middle bit. So we had our starting point, calculation, then ending point. But what does this mean? If I told you this, what can you tell me about f of g? It's injective. Hands up if you think this was easy, relatively easy. I mean, like, easy enough if I put in a test, you'd get it eventually. Okay, no, that's right. No, I just want to get an idea. Yeah, f of g is injective. Good. Okay. So we did this one for injectivity. You don't need to take photos. It's uploaded afterwards. Okay. Save you the phone storage. Okay. Number 2. Yeah, I know. A lot of photos of yourselves and Instagram and all that. Okay, no. Lectures are recorded. It's on YouTube. The actual PDFs are uploaded right after. You don't need to take photos. Also, when you take photos, they get lost, right? You take one photo, then you take 10 selfies later, your notes are gone. Okay, so number 2, this one's going to be for homework. Same idea as number 1. Okay, so let f from a to b and, it doesn't really matter. Okay, so f to a to b and g b to c be surjective functions. Prove that. So we're going f a to b, g from b to c, so it's g after f, right, for the ordering. Does everyone see the ordering? Okay, this one comes second, so we write it first. It's weird, but that's just how it goes. So g of f is surjective. And you're going to set it out exactly the same as before. So you write what's given, f and g are surjective. If you don't know what that means right away, you put your definition here. Also, you get part marks for all of that. Then, need to show. What do we want to show? Do your calculations and put a little conclusion. Everyone understand? Good. Okay, so that'll be for homework. And then one more for homework, and then we'll do the other one in class. Let f and g be odd functions. Prove that f of g of x, so we take the composition, so any odd function, you take the composition, it's also odd. Okay, same idea. Given f and g are odd, here we don't need the domain and the range, we just need the condition to be odd, right? F of minus x is minus f of x, g of minus x is minus g of x. So you put that down as your given. You put this down as your need to show that that's odd. Do a calculation. You should end up with minus f of g of x. Does everyone understand? Okay, so you do that one. And then this next one we'll do in class. Okay, so number 4. Let f from a to b and g from b to c be 2 functions. Okay. So I'm not saying what they are, they're just 2 functions. 4.1. Assume g of f is injective. Okay, so it's a little bit different to what we did before. So before we were given the individual parts were injective. We had to show that the composition was injective. Now we know the composition is injective. What we want to show is that f must be injective for it to work. It's a little bit more thinking, but it's not too bad. Prove that f must be injective. Yeah, now this is very interesting, right? We've got any two functions, any two. If the composition is injective, then f, the starting function, must be injective. But we'll see in part 2, g does not need to be injective. It's only the first one. Okay, so for part 2, prove that, or provide an example. G does not have to be injective. Okay. So if the composition is injective, you don't need both of them to be injective, just the first one. But in the previous one, if you do have both of them being injective, then the composition is injective. Okay, just read that a couple times just to understand which way we're going. So let's start with the first one. So we know that the composition is injective. We want to show that the first one is injective. Okay, so 4.1. Proof. Let's just draw a little diagram just to see what we're working with. So we're going from A to B to C. We've got the composition chain. F takes us from A to B. G takes us from B to C. And we know that the whole thing, the composition, is injective. Now we want to show that just this first one must be injective. Second one does not need to be injective. Now, what does it mean for the whole thing to be injective? We know the definition, we can write it down. So, given g of f of x is equal to g of f of y, then x equals y. That's what it means for the whole thing to be injective, and we know this is true. That's given to us. So what do we need to show? Okay. Anyone like to volunteer? What do we put down? Go up a little bit so you can read it again. So it's whatever, let's prove that. That's what we want to show. So this is in words, right? Prove that f must be injective. So what do we write down as a math statement? I'll give you if, yep, 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 yeah, then,
yes, x of y.
Perfect. That's what we want to show. So we should end up with this as our last line. If we end up with this as the last line, then we're good. Okay. So let's check, right? We want to check that f is injective. So let's start with that. Okay. Now, I will give 5 points for the next quiz coming up to whoever can tell me the next step. It's a little bit more difficult than what we had last time, but if you know it, I'll give you 5 points. First one to put their hands up and it's correct, you get it. Okay, so we want to show this, and we're given that. There's only one thing that we can do with that given information. Yeah.
Since we have given that g of f
Yes.
is equal to g of y,
Yes.
then x is equal to y.
That's right.
And then we need to show that f of x is equal to f of y, then x is equal to y.
That's right.
So as on the statement above that we have given,
Yep.
we know that x is equal to y.
No, we don't know this yet.
That, on that above.
Yeah, this one we know. Yes, that's right.
We know that x is equal
Yes,
to y.
that's right. That's right.
And then the statement that we've written now.
Yes.
F at x is equal to 1.
Yeah.
We said f into x
Yes.
is equal to f into y.
Yeah.
This x and y, we know that they are equal.
We don't know that yet.
But
We
we said that x is equal to y.
No. That's need to show. We still need to show that. We don't know it yet. This is our goal. This is need to show.
On the given one, say.
Yeah, the given one is g of f. It's not just f. I'll give you one more chance and then we'll go to him. Okay. Yeah.
I think since we have been given that
Yep.
g after f of x,
Yep.
we got to g after f of y.
Yeah.
Then I think we need to apply the same logic here to say g of x, g of f
Yep.
of x
Yeah.
is equal to g of f of y.
Very well done. Very nice. You get your phone, but I'm just what you should know that. Very nice. You almost had it. Very, very close. You had the two steps, you just had to put it together. Yeah, very nice. Extra 50%. So you can do half the quiz and then fall asleep. Yeah, very good. So we're going to apply G on both sides. Did everyone hear what he said? Okay. So we're going to apply G on both sides. Okay. And then?
And then we're going to continue with f of x is equal to f of y because we know that g. Yeah, it is.
From the given.
Yes.
Yeah, from the given. Very good. So this we can write as g of f of x equals g of f of y, like he said, from the given. So the reason is just given, right? So we know that already. Yeah, and then we know x equals y. And let's just conclude this. So what did we start with? We started with f of x equals f of y. So we took that as our starting point. So we put that down. Then we did some calculations. So remember equality, it's all the same. So equal, equal, equal. And we ended up with this. So if that, then a bunch of stuff, but more importantly, then that last line. We put a big box around this. What does this mean? F is injective. Very good. Nice. Done. Easy. Fairly easy. Okay. Everyone understand? Okay. Now, last bit, and then we'll leave it at that for today. The 4.2 part, provide a proof or counterexample. We're going to do an example. If you want to try a proof, you can, but that's a bit much. An example is fine. That shows that G does not have to be injective. So we're going to do an example with F and G such that F is injective, the composition is injective, but that G is not. Okay, so we need to think of some idea. Or you can do a picture with that, the circle and the dots. You can do it like that as well. Okay, so let's say we need some F. And we need some G. This one must be injective. This one is not injective because we want to show it doesn't have to be. And finally, we want to show that G of F is injective after we do the composition. Yeah, so maybe we need to think about it for a little bit, but it's not too bad doing an example. So we have F is injective, G is not injective, but when we do the composition, it becomes injective again. Okay, so we need to think about, some examples. So let's draw a couple pictures just to see what we can work with. or maybe something like that, just to have an idea. So F must be injective. So that's this first one. So this first thing must be injective. So we can only do 1-to-1. There's no other way. Okay. Now we need some way of going from here to here that's not necessarily injective, but the whole thing becomes injective. It doesn't have to be surjective. So don't think we have to use all the points, right? It can all go to 1 point if you want. But when we follow all the lines from beginning to end, it must be injective. So let's just play around a bit. So this one, pick something. First one. Okay, now let's go with it. This one, 1, 2, or 3. Someone says 2. Let's go with 2. And then this last one. Remember, we're aiming for something not injective. So it needs to be one of these two that we chose already. So let's pick. Over here. So this is just some example. Let's check. Maybe it works, maybe it doesn't. We'll fix it up a bit in the next picture. Okay, so we're checking for 1-to-1. So let's go with the first one at the top there. 1 and it goes to 1. That's fine. That's all fine. Here we have an issue. Here we've got 2 of them. We follow the lines, they go to 1. So it's 2-to-1. That's not injective. That doesn't work. So we need to change something a little bit here so that it does become injective at the end. So this middle part doesn't matter so much, but we want 1-to-1 after we look at the combined lines. A small thing we can change, nothing too dramatic. Maybe another 5 points will be some encouragement. Or 10 points. Let's say 10 points. Okay, you seem happy with 10 points, we'll do 10 points. If you can figure it out, I'll give you 4 marks for the next quiz. Okay, the lectures are recorded, but don't tell anyone. Okay. No, it's fine. We can do whatever we want. Your other lecturers don't give you points or anything. No. Oh, that's not nice. Okay, yeah, 4 marks for the next quiz if you can figure this one out. So if you can figure this out, I trust that you know how to do the proof already, which means you could have done the quiz. So it's all fair. Yep.
So let's look at the question what is being required for us to do.
Oh, okay. So we want to have this function from A to B to C so that it's 1-to-1. So here, notice that top line, 1-to-1, the top line. But this line, these 2 lines, is 2 over there. And then you follow the lines, they go to 1. So it's 2-to-1. That's not injective. So we want to change the lines a little bit. It doesn't have to be too much. Just change it a little bit so that it becomes 1-to-1. Yeah, you can change it around. You can add more dots. Just change it a little bit. Right. I don't want like 10 lines going to 10 lines, right? That's too much. So a couple lines to a couple lines so that it's 1-to-1 in the end. Yeah. You got an idea? Okay. Come draw it, and then everyone can see. Yeah, just draw the picture, and then everyone can see. You have to go to the middle one first. So put the dots. Yeah, so put a dot there. Put a dot there. And a dot there. You need one more there to go to. No. No, on the line. For the dots. So they can see the dot there. Yeah, okay. So we got that. Good. Yeah. Yeah, let's just connect the dots to see it. Yeah, that's. But then that's not injective anymore. Yeah, this one is now 2 to 1. This must go to something else. Yeah, you can rub that bit out, make it go to something else. Okay. Is that correct? Okay, remember what we said. G must be not injective. His G was injective. Okay, so that doesn't count. Yep, you got an idea? Come up. Remember, it's 4 marks for the whole thing, not just. You can just skip the day if you want. Yeah, it's not too easy. So if you can do it, it's worth 4 marks. Okay, so you got a bunch there. Okay. But both are injective. Yeah, no, that doesn't. Okay, you were first.